Hello and welcome back to Pre-Algebra. This is the course review where we take the first 12 videos that you might have seen and compress them into 5 questions. So this combines many of the ideas that you must have seen in those 12 videos. The first question is all about fractions. So calculate the following expression. Now there are many different operations in this one, such as divisions and multiplication, addition. There's an exponent in there. And of course we have to remember all the stuff that we did with fractions. So this looks complicated, but if you remember, there is an order that we have to apply all of these operations, which I've written here. Start with the brackets and then do the exponents, division, multiplication, addition, and subtraction. So my first question is, are there any brackets? Well, the answer is yes. There's one bracket right at the end, right here. That's where we would have to focus first if the thing inside of the brackets needed to be simplified. Now, 2 over 3 is about as simple as it's going to get. So I'm going to say that the brackets are finished. But the next one, exponents, well, I see an exponent right here. This means 2 over 3 to the power of 2. Let's apply that exponent. So when doing so, make sure to copy everything, even the stuff that did not change, into the next line. So 3 over negative 2 times 4 over 7 plus negative 3 over 5 divided by this. So what is 2 over 3 squared? That's like 2 times 2 over 3 times 3. It's 2/3 times 2/3, more or less. So we need to figure out what this exponent is before we can move on. So what is that? Well, if you remember, multiplying two fractions is the simplest thing to do. All you have to do is multiply the two numerators and multiply the two denominators, and we're done. So next we can look at divisions. So we've finished the exponents here. Let's look at division. I see a single division at the very end, and the way that you divide fractions is by flipping the second fraction and multiplying. So all of this stuff stays the same. And I'm going to flip the 4 over 9 to make 9 over 4. And now instead of a division, we have a multiplication. That's about it for this division, because the next step is going to be multiply. So we've done the divisions. Next, we have to multiply. So 3, let's try this multiplication first. 3 times 4 is 12 over negative 2 times positive 7. So if you recall, a negative times a positive makes a negative, and 2 times 7 is 14. Now, what is a plus minus? That would make a minus. 3 over 5 times 9 over 4. That would just be 3 times 9, the two numerators, which would be 27, over 5 times 4, which is 20. So this is starting to look a little bit more simple. Now, before I go any further, because I'm a little bit lazy, I prefer to deal with smaller numbers. So I'm noticing that 12 over 14 can be reduced. If you realize that both of these numbers can be divided by 2, this then becomes 6 over 7 minus 27 over 20. So we've done the multiplications. There are no additions to do, so I'm going to consider this finished. There's only one subtraction left to do, which is the first fraction minus the second fraction. Now, we have a problem. Hold on. We can't just subtract these numbers because 7 and 20 are different denominators. So we have to make them the same denominator. And the easiest, the quickest way that requires the least amount of thought is to just multiply them by each other. So 7 times 20 And if you multiply the bottom number, you have to multiply the top number by the same thing. So 6 times 20. And also this 20 over here has to be multiplied by 7. And that will result in the numerator also being multiplied by 7. So I'm going to need my calculator for this one. Although 6 times 20, that makes 120. 7 times 20 is 140. 140. So that means 20 times 7 would also be 140. 27 times 7, I have no idea. So I'm taking out my calculator and doing 27 times 7, 189. All right, so what is 120 minus 189? That would be negative 69 over 140. Now, why is it negative? It's because we're taking a small number that's positive and subtracting it by a bigger negative number. So the negative ends up winning in the end. And the difference between those two, between the 120 and the 189, is 69. Now, as far as I can tell, this cannot be reduced because 69, we could divide this by 3, let's say, but this one cannot be divided by 3. And I can't think of any other number that would work. So I'm going to consider this the end of this question. So this must be the answer. So this can be complicated, but if you stick to BEDMAS, you shouldn't have much trouble. Just don't be afraid to do many, many, many lines of work. You know, just copy everything down into the next line, but change only one thing. I see a lot of students make the mistake of trying to do 5 steps all at once, and you're 5 times more likely to make a mistake if you skip 5 steps. So don't be afraid to take your time. Write as many lines as you need to write. Just, you know, get to the answer safely. And here's another one. Write the following in scientific notation. So this one forces us to learn a lot about exponents and their rules. So here is a quick reminder of how exponents work. For example, if we had 2 to the power of 2 times 2 to the power of 3, in this case where we have the same base twice, and they're both raised to some sort of exponent, some sort of power, the answer would be 2 to the power of whatever 2 plus 3 is. So you just add the 2 exponents, so 2 to the power of 5. Now, people often get this confused with the other rule, which is whenever there's a bracket involved. Whenever there's a bracket separating the 2 exponents like this, the answer becomes 2 to the power of 2 times 3, which would be 2 to the power of 6. So be very careful with these. Now, with that in mind, let's try to make some sense out of this. So sometimes you can be a little bit clever with these and make your answer a bit more simple. Here's the first thing that I'm noticing. 3 to the power of 2 to the power of 3. Let's ignore this first piece for now. We can just deal with this later. It's really this 3 squared to the power of 3. That looks very similar to the second example that I gave here, where there's a bracket separating the 2 exponents. So this would just be 3 to the power of 2 times 3. And we know that 2 times 3 is 6, so I'll just rewrite that in the next line. And this is what we have so far. Let's remember a couple of other rules, which would be some special cases of these exponents. Now let's say that I had 2 to the power of negative 3. Anytime you have a negative exponent, it's just like having 1 over 2 to the power of the positive exponent. And also, if you ever had a square root, that's the same as having the number raised to the power of 1 over 2. So we're going to use those 2 ideas for this next part. First off, I recognize that 9 is just 3 times 3. So I'm going to actually write this as 3 squared in the place of the 9. Now this is just a strategy that I like to use because I want everything to be a 3 in the base. You'll see why this is useful later. Oh, look at that. There's another set of brackets separating exponents. So if we know what 2 times negative 8 is, we can answer that here. 3 to the power of negative 16 times 3 to the power of 6. Now this example here, 3 to the minus 16 times 3 to the 6, looks an awful lot like our first example here, where the base repeated itself and we just have 2 different exponents, or the same exponent would work, but they're different in this case. We would have to add the exponents. So this is negative 16. This is 3 to the power of negative 16 plus 6. So we're adding those 2 exponents. And well, negative 16 plus 6, negative 16 is 16 is a bigger number and it's negative. So the negative wins. The difference between 16 and 6 is 10. So this would make negative 10 because the negative is stronger. Now remember what I said about that square root. A square root is the same as raising something to the power of 1/2, as we've seen here. This will be our next step. 3 to the negative 10, all raised to the power of 1/2. Okay, well, what is this going to make? The bracket is separating 2 exponents. So we're more or less just multiplying the 2 exponents. I'm going to make this bigger just so you can see what's happening here. 10 times 1/2 should look familiar to you because 10 can be made into a fraction if you just put it over 1. And now we just have to multiply 2 fractions together, which is multiplying the 2 numerators, 10 times 1, which makes 10, and the 2 denominators, 1 times 2, which makes 2. Now, this can be reduced, and in fact, this is just 10 divided by 2. Any fraction is just the top number divided by the bottom number. So 10 divided by 2 is 5. So, oh, don't forget that this whole thing is negative. So really, I should have put a negative onto all of these. So now our answer is -5 for the exponent. So in the place of this complicated exponent that we had, I'm just going to put 3 to the power of -5. And this is looking a lot more simple. All we have to do now is remember, what is a negative exponent? A negative exponent is just, all you have to do is flip the fraction, or you do 1 divided by the base to the power of the positive exponent. So 3 to the power of -5 is the same thing as 1 over 3 to the power of 5. Now, perhaps this could be our final answer, or you could do 3 to the power of 5, which is 3 times 3 times 3 times 3 times 3. I will shamelessly use a calculator for this because I don't know the answer in my head. 3 times 3 times 3 times 3 times 3 equals. I feel like I should have known this one, but I didn't. So 3 times 3 times 3 times 3 times 3 is equal to 243. So our final answer is 1 over 243. So this should cover pretty much every scenario that you might run into, mostly, of exponents. And so as long as you can stick to these 4 examples or these 4 rules, you can apply them at various times. So we can go from something very complicated to this. Now, actually, the question was asking something a little bit more. It was saying, write the following in scientific notation. So that's actually going to be our next step. So we figured out what the value of this expression was. I'm going to write it up here. 1 over 243. Now this part will require a calculator. Let's put that into the calculator. 1 divided by 243 it's going to give you some decimal number. 1 divided by 243. I'm getting 0.004115226. Now this does keep going, but my calculator stops here, so we'll say that it stops here for now. Scientific notation requires us to have some number times 10 to the power of some number. So the question is, what do I put in those two boxes? Well, let's look at the first digit that's not 0. So this 4 right here. And think to yourself, if the 4 was at the start, right before the decimal place, how many spots does it need to move? Well, 1, 2, 3. So it has to move 3 to the right, or it has to become 3 orders of magnitude smaller than what it was if it was the 4 over here. That's one way of looking at it. There's another little trick that makes this require less thinking. Just think, how many zeros do you see here before the 4? And I see 3 zeros, including the one that's before the decimal place. So that's important. We need to count this 0. So 3 zeros. And the number is now very small. It's 0.00 something. So it's a very small number. So if it makes the number small, you put a negative in the exponent here. And how many zeros? 3. So a negative 3 goes there. Next, all you have to do is copy the numbers that start appearing after that 0, after the last 0. 4, 1, 1, 5, 2, 2, 6. And for scientific notation, you always have to put the decimal after the first digit. Why do we have to do that? Well, we don't want to have two different answers that mean the same thing. So scientific notation, you'll never see two different scientific notations that equal the same value. And that's why it's more standardized, I suppose. So the standard is to have one digit and then a decimal, and then however many digits that you choose to have afterwards. This number in the exponent will take care of the rest. So that should be our answer. 4.115226 times 10 to the power of negative 3. Let's look at the next one here. Find the area of the shaded region. So this one looks a little bit complicated, but it might not be so bad. Here's what I noticed at the start. This whole thing is separated into seemingly similar pieces right along here. I'm going to study one of these pieces. And once we understand a little bit about one, maybe we can apply this to the rest. How big is the orange rectangle that I just made? Well, it would be half of this width. The width is 5 down here. Half of that would be 2.5. And how tall is it? Well, half of this entire height, which is 4, the entire height is 4, so half of that would be 2 meters. So at most, the rectangle itself would be like this, 2.5 to 2. At most, it could have an area of the length times the width, or the width times the height, or, you know, they all mean the same thing, really. Multiplying these two dimensions together. 2.5 times 2 is 5 meters squared. That's the height, or that's the area of the rectangle. But not all of it is colored in. So we might have to subtract a certain piece. Well, there is some symmetry involved in this. And by symmetry, I mean this thing looks like it could be mirrored. Check this out. This rectangle that I just drew here in yellow has a height of 0.5 meters. So does this one up here. They both have exactly that same height. One of them is colored blue, the other one is not colored blue. And all that's left here is one triangle that's colored and the other triangle that's not colored. It stands to reason that half of all the triangles are colored. I'll write that down here. Half of the triangles are colored. And also half of the rectangles are colored. Now, also, if you look closely, the triangles, they're the same. They're the same height, the same width. Everything's the same about those two triangles that I made up there. And the rectangles are also the same. So what does that tell us? It tells us that half of what is in that rectangle, the big rectangle, the 2.5 by 2 rectangle, half of it is colored. So half the area of, this weird piece that we had here, half of it, it's going to be half of the area of the full rectangle, or half of the 5 meters squared. So what's half of 5? Well, that's the same as 5 divided by 2. It'd be 2.5 meters squared. This covers one of these rectangles. And if you check the other two or the other 3 rectangles, this one, and this one, you'll see the exact same pattern is emerging. Exactly half of each of them have been colored. So if one of the rectangles that's partially colored has 2.5 square meters of coloring, and there's 4 of them, then the total area would just be 4 times the area of that one piece, or 10 meters squared. So we can save a lot of work if we strategize. Otherwise we would have to calculate all the areas of each triangle and each rectangle, and then subtract all the pieces that were not colored in. It could have been a lot of work, but you can really, if you're creative with these, you can take a lot less time. Here's the next one. You're given a density of 0.7 times 10 to the power of 3 kilograms per meter cubed. Find the mass in kilograms of the following wooden oak table. So this entire table that's drawn here is made out of oak. Oak has a certain density, which is mass per volume. And I just want to know how many kilograms would this thing be. So interesting. If we look at this density, it says that it's so many kilograms per cubic meters. So kilograms is a unit of mass, or how heavy something is, more or less. And that's not exactly correct. If you study physics, you'll understand how that mass and weight mean 2 different things. But for now, we'll say that they're the same thing. Meters cubed is a measurement of volume. So it looks like we'll have to calculate the volume of this entire table, and then we can consider the density and think about how much mass that's going to make. So let's do that first. In order to calculate the volume of this table, we have to know what a rectangular prism is and how to calculate it. So a rectangular prism, it's just a shape that has rectangles in every direction. The way you calculate it is, if this is the base, the length, and the height, the volume is just the base times the length times the height. It's not very complicated. You just multiply all the lengths together. So this table, I'll break this up into pieces here. So the tabletop, I'll call this piece number 1. This would be piece number 2. Well, all these legs are the same design, so I'll call them all number 2, because there's no sense in calling them 3 and 4 and 5, because they're the same thing. So the area, or sorry, the volume of the first piece is going to be the base of the first piece, which is 6 feet, times the length, which would be 3 feet, times the height, which is 2 inches. Uh-oh, this is going to lead to a problem because we'd rather all of these be the same unit. So we have two choices. We can either convert all of the feet to inches or convert the inches to feet. And in order to not get into decimals just yet, I'm going to choose to convert the feet to inches. In order to do that, we need to realize that 1 foot is the same as 12 inches. If you're not sure about this, please look it up. You can find all sorts of conversions online. And I recommend you get used to either memorizing some of the more convenient ones or just knowing how to convert something and then rely on looking up the conversion online if necessary. Depending on the course you're in, perhaps you need to memorize some. But there's so many that exist that, you know, good luck memorizing all of them. It's not an easy task. So 1 foot is the same as 12 inches. I'm curious to know what 6 feet would be. Well, here's how to convert. You times it by a fraction that has feet on the bottom to cancel with feet on the top and inches on the top. And you just have to copy the numbers that you see here. So 12 is with the inches, so I'm going to put 12 here. 1 is with the feet, so I'll put 1 here. So it looks like all we have to do is 6 times 12 over 1. I won't even bother with the 1 times 1. We know that's going to make 1. So 6 times 12 is going to be 72 inches. The same can be done with the 3 feet. So we realize it's going to be times 12 inches over 1 foot. The feet cancel. 3 times 12 is 36 inches. So let's go ahead and make that change in our calculation. The volume V1 equals 72 inches times 36 inches times 2 inches. 72 times 36, I'll need a calculator here. 72 times 36 times 2 equals 5184 inches cubed. And I put inches cubed because it's inch times inch times inch. So we have 3 occurrences of inches. That's V1. Now let's look at V2, which I only need to really learn about one of the legs of the table. And then we just multiply that answer by 4 when we get the total, because there's 4 legs. How tall are these legs? Well, it's a little bit tricky for this one because the entire height of the table is 3 feet, but that includes the thickness of the tabletop, which is 2 inches. So that means the height, let's see here, the base would be 4 inches, the length is 4 inches, but the height is going to be a bit different. So 4 inches for the base, 4 inches for the width. The height is going to be 3 feet minus that 2 inches. You know, it's the whole thing except for the thickness at the top. That's not part of the legs. We already accounted for that when we did the tabletop. Well, we can recycle some of our work because we learned a while ago that 3 feet is the same as 36 inches. So V2 is equal to 4 inches times 4 inches times 36 inches minus 2 inches. If you remember briefly BEDMAS, it says that you have to do the brackets first, meaning we have to figure out what 36 minus 2 is, which shouldn't be too bad. This will make 34. And now we multiply. So 4 times 4 times the 34, 544 inches cubed. So we have V1, we have V2, and now we have to get our total. V total volume. Well, there's only one of the first piece. There's only one tabletop, but then there's 4 legs on the table. So V1 plus 4 times V2 will give us our total. So V1, 5184 inches cubed plus 4 times 544 inches cubed. Remember to do the multiplication first, so I'll take my time with this one. Copy this part down. What is 4 times 544? My calculator says that this is 2176. Now let's add these two together. Plus 5184, 7360 inches cubed. So we're on to something now. We have a total volume of 7,360 inches cubed. We're not quite there yet because we need, first of all, if you recall, our density is in cubic meters, meters cubed. That means we have to convert all of these inches into meters. I'll have to write that on another step up here. So 7360. Let's try it up here. Whoops. V total equals 7360 inches cubed. We need to remember 2 things. One, that 1 inch is the same as 2.54 centimeters. And also 1 centimeter, or actually 100 centimeters, is the same as 1 meter. Now let's think about what an inch cubed is. I'll write it out the long way. This is actually saying an inch times an inch times an inch. Now when converting this, if I want to get rid of inches, I'll do the first one here. 1 inch goes down here. 2.54 centimeters goes up here. I'm just copying straight from this because I know 1 inch is the same thing as 2.54 centimeters. That will successfully cancel 1 of our inches. So be very careful, and I see a lot of people overlook this detail. When you have inches cubed, you have to convert it 3 times to get the effect. So I have to do another 2.54 centimeters per 1 inch. That will cancel the next inch, and then times 2.54 centimeters over 1 inch. That will cancel the third and final inch. So in order to not make this too messy, let's figure out what this makes. So 7360 times 2.54 times 2.54 times 2.54 equals 120,608.791 centimeters. And there's 3 of the centimeters. I'll write them out like this. We could put centimeters cubed instead of 3 of the centimeters, but I'm going to write it like this because I'm thinking about what we're going to do next. Convert all of these centimeters to meters. Now to do so, centimeters are up here, so we need to cancel them by putting them down below. Now we realize that 100 centimeters is the same as 1 meter. So 100 centimeters, same as 1 meter. So this means that we have to divide by 100 a total of 3 times. That's one way of looking at it. So this is 120,608.791. Centimeters will have canceled with each other. Divided by 100 times 100 times 100. Or 120,608.791 over whatever 100 times 100 times 100 makes, which should be 1 with 6 zeros, or a million. Now let's do this division. I'm just going to keep a couple of decimal places here. Let's say 608. Let's round that up. 9. Something like this. This would be, oh, and what's left over? We would have meters times meters times meters, or meters cubed as our answer here. So this is the volume. We're still not done. We've converted the volume into cubic meters. Now we have to apply this density to figure out how many kilograms we have. Now you can usually just let the units guide you with this. So 0.7 times 10 to the power 3. So oak wood is 0.7 times 10 to the power of 3 kilograms per meter cubed. So all I have to do now is times this by, I want to cancel out the meters cubed and just have kilograms left over. I'm going to times it by the total volume that we have, 0.120609 meters cubed. So now you can see why I had to get them in the same type of unit, meters cubed, because now the meters cubes will cancel and we'll be left with kilograms. So 0.7 times 10 to the 3, let's remember what that makes. That would be 0.7 times 1,000, 10 times 10 times 10, and then times the 0.120609. And the only unit left is kilograms. And these ones in the denominator, I'm not going to bother with them. I know they're just ones. They don't do anything. So 0.7 times 1,000 times 0.120609. I'm getting 84.4263 kilograms. Something like that. We can round that, let's say 84.4 kilograms. This would be how much mass the table has. So it's all about getting the same units. So we started off in feet. We had to convert all of those feet into inches, all of the inches into centimeters, all of the centimeters into meters, and then all of the meters into kilograms using the density that we were given for the material. And that should be our answer. Here is the last question. So light travels at about 1.86 times 10 to the 5 miles per second. On average, Earth is exactly 1 AU. So AU stands for astronomical unit. I'll write a small note about that here. So 1 unit, or 1 AU is 1 astronomical unit. So it's 1 AU away from the sun. How long does it take light from the sun to reach Earth? So we first need to know what 1 astronomical unit means. So a couple of scientists must have got together at some point and they determined the distance between the Earth and the sun, but that distance is changing a little bit as time goes on. So throughout the year, sometimes the Earth is closer to the sun and other times it's a bit further away. But on average, it's about this far away. So 148.47 million kilometers. And we're given the speed of light in miles per second. So our units are not exactly compatible. We'd have to either convert the miles to kilometers or convert the kilometers to miles. So before we decide which one to do, let's consider the conversion between miles and kilometers in general. So let's say, just for example, I wanted to take my miles and convert them to kilometers. the way that you might have seen in the last video or in one of the previous videos on conversion, we'd have to go from miles to feet, feet to inches, inches to centimeters, centimeters to meters, and then meters to kilometers. So that's going to take quite a bit of time. And you're probably asking yourself, is there a better way? Yes, there is. So if you happen to know the direct conversion from miles to kilometers, then this becomes a lot easier. So this is something that could be looked up, but it turns out 1.86 miles is the same thing as 3 kilometers. Well, that's kind of a coincidence because the speed of light seems to have this 1.86 in it. And then there's the 10 to the 5. But that might be the easier way to go because I'll just copy that number down here. So the speed of light is 1.86 times 10 to the 5 miles for every 1 second. And we know that 1.86 miles is the same as 3 kilometers. That cancels perfectly with the 1.86 canceling the 1.86, the miles canceling the miles, and all we're left with is kilometers and seconds. So we have 3 here, but don't forget about this 10 to the power of 5. So 3 times 10 to the power of 5 kilometers, and then we still have seconds down here that has not canceled, so we need to keep that. So 3 times 10 to the 5 kilometers per second. So another way of thinking about this is every 1 second, 3 times 10 to the 5 kilometers have been traveled if we're talking about light speeds, so something traveling at the speed of light. Another way of looking at that is when we're dealing with just light, when we're dealing with light or light travel, 3 times 10 to the 5 kilometers is equal to 1 second. They're the same amount of traveling. That's one way of thinking about it. And that's going to be useful if we try to convert these astronomical units, which are currently in millions of kilometers. So first, let's think about millions of kilometers. Well, how much is a million? Well, a million is 1 with 6 zeros. So a quicker way of writing that would be 10 to the power of 6. That just means 1 and then 6 zeros after it. Kilometers. Let's go ahead and do this conversion, which would say that we multiply by some fraction so that we cancel out the kilometers. So kilometers must go down here, and seconds would have to go up here. Now for light travel, we already established that 3 times 10 to the 5 kilometers is the same as 1 second. Or that's how long it takes to travel 3 times 10 to the 5 kilometers. It takes 1 second. This is going to be pretty nice because the kilometers now cancel. And the 10 to the power of 6 and 10 to the power of 5, I'm going to put those aside for a moment. You'll see that there's a lot less work that we need to do than you'd expect. 148.47 over 3, because the 3 did not go away. Neither did this 148.47, times 10 to the power of 6, and the 3 is times 10 to the power of 5. So in other words, it's this many seconds. Well, let's think about our property of exponents. I'll leave this part alone. 10 to the power of 6 divided by 10 to the power of 5. It's as though you were subtracting the exponents. Well, 6 minus 5 is just 1. So 148.47 over 3 times 10 to the power of 1. And 10 to the power of 1 is just 10. So now we can get a final answer for this, I suppose. Well, let's actually put this into a fraction. So this is over 1. 148.47 times 10 is 148.4.7 divided by 3 times 1, which makes 3. Don't forget the seconds like I just did there. And now let's do this division. So 1,484.7 divided by 3. It's 494.9 seconds. So this seems to be the amount of time that it would take for light to travel 1 astronomical unit. And we know that 1 astronomical unit is about the distance between the Earth and the Sun. So light can go from the Sun to the Earth in that many seconds. That number is quite a bit of seconds. I may be more interested in finding how many minutes it would be. So we can continue. Let's try figuring out times. Well, let's cancel out the seconds and put minutes in its place. So as long as you know how many seconds are in a minute, or minutes in a second, although seconds in a minute would be easier, we can do this conversion straight right away. So 60 seconds happens to be the same as 1 minute. So that will cause the seconds to cancel, and we're left with 494.9 divided by 60 minutes. Then all we have to do is figure out, well, how many minutes is that? Put that into your calculator. I'm getting about 8.25 minutes if you round at the nearest hundredth right here. So that's how long it seems to take. It takes about 8.25 minutes, which is surprisingly long. You'd expect light from the sun to reach Earth pretty quickly, but it actually takes a full, more than 8 minutes. And that just goes to show you how incredibly far away the sun is from the Earth. Anyways, that is our review of pre-algebra. I hope this made sense, and I will see you in the next course, which will be Algebra 1. See you there.